brutal. Like seeing these lines, like it's insane.
I haven't watched it.
Don't do it. Actually, like five people there, like.
Which movie is your next?
It's gonna be fun.
Easy. Quite a lot. Let's start it. Welcome. Please be seated, and then we're gonna start. Today we'll go into the question of discounting. Discounting has been quite a disputed area in the past in the environmental economics literature and in policy work. And one of the reasons is that if you change the discount rate, your results change a lot when you are evaluating long-term projects. And the typical very long-term project is climate change. It's a problem that has effects over many centuries, and so the discount rate is going to matter a lot. And so we're going to have 2 hours about how to discount. And they will we've already seen actually the basic rule for discounting. So that was the Ramsey model. We've seen that in week 1, but we'll build on that, and we'll also need to take into account uncertainty. So we don't do full stochastic optimization in this course. That would be way too technical. But we're still going to do, with some simplifications, bring in uncertainty. So we'll start with the basics of what is discounting, what is the net present value. Then we'll go into the normative approach, the Ramsey rule, then the positive approach, opportunity cost of capital, positive being more descriptive, what can we learn from returns in the market, and go from there and deduct from there how people discount in practice, or how investors discount in practice. And then adding this uncertainty more properly, declining discount rates, and then we'll say something about discounting the environment where it might be the case that you're discounting something that has a shadow price or a price that changes over time. What if we're discounting like species, but actually the willingness to pay for corals might be increasing over time? And so if we then value the corals, saving corals, we need also to take into account that people will value that more. And another way of saying that is you should then use a lower discount rate. But we'll treat that properly. We will also treat the last point in the seminar. So yeah, what's the problem that we start with? So you may have a nuclear power plant, very costly. The first 5 years, you're actually building it, no income. Then it works, you have positive cash flows, and then there might be decommissioning costs. And so how do you assess this? So you cannot just add these things up because time matters. You should take into account that costs in the future may be valued differently. Here is the similar example for climate change. So climate change in this case, this is a simulation for DICE. So initially you have a lot of costs. So if we save the climate, the current generation is worse off. We have all the cost of the green technologies, but then later our kids are gonna be much better off. They avoid the warming. Yeah, so maybe it's not obvious why climate change is avoiding climate change is costly. I see you like, do I believe that? So yeah, we'll see that next week, no? But the idea is that if green technology would be really cheaper, we would already do it. And so most economists would assume that green technology is more expensive than the brown one, and that you therefore, even if there is learning, so that therefore a world without oil is gonna consume slightly less than a world with oil if you abstract from climate damages. Basically saying the marginal return to oil is positive. That means that if you avoid it, you're gonna have costs. But we'll come back to that. The point here is just, what if you have short-term costs and long-term benefits? How are you going to assess that? Little joke, New Guyana, population 562, 2,150 feet above sea, established 1951. So we have a total of 4,663. So that obviously doesn't make sense. So, so it's going to be about how pricing time. We have this guy thinking, so he has this option of eating a pig today, but he can obviously also like not eat it. Then the pig has small piglets and he'll have more pigs next year. So what's the trade-off? But this already indicates that by waiting, you might have more, yeah? And so let's remind ourselves of a few concepts. You probably have seen this in finance. So your bank, imagine you have 2% interest rate on your bank account. Then you put £100 on your bank account, you'll get 102 next years. After, so how do you get there? This you multiply by 1 plus the discount, plus the interest rate. Now you leave it on the bank, so now you get 104 and a bit, because the interest from year one is also now getting interest. Yeah? So that's how you get to this larger number. And so then you can also ask the question, if I have 100 in 2 years, how do I value that today if I have this possibility of putting it on an account? And so then it's worth only 96.11, because if I put 96.11 today on the bank, I get the 100 in 2 years. Yeah, so that's now why it's in the denominator. For the whole lesson, we're going to assume we're going to work in real terms. So that means that if there is 2% inflation, we have subtracted that. So we've said after inflation, this bank account gives you 2, meaning the nominal interest rate might be 4. Let's do, okay, so we abstract from inflation. Inflation is a relatively easy thing. So we work in constant prices. Now, this is just for one cash flow. How do I value 100 pounds that come in 2 years? You can apply that for all the cash flows related to one project, and so then you get the net present value of your project, all the benefits, net benefits discounted in each point in time. It's the net present value of your project. And then you can, with the same equation, ask another question. So if you say, what is the discount rate that is required to get break even, to get a 0 net present value, we call this discount rate the internal rate of return. So the definition of the internal rate of return is the one that sets the net present value to 0. Questions? Good. Then, for simplicity, I've started with discrete time. Continuous time is a bit easier once things get more complicated. So here is the equivalence. So I had derived this discount rate in the preceding slide. Now, this is actually just a power function of t. And so if we're working in continuous time, we're going to write it this way. Yeah. Again, this is a power function of t. And so they're equivalent provided that I slightly adjust my discount rate. Yeah. So they are very close. The one is a Taylor approximation of the other, but they're not exactly the same. But if I switch to another number, then the function is exactly identical. Okay, so quick reminder, what is a Taylor approximation? You must remember this is also explained in the supplementary notes. And so if I take the first order expansion, the Taylor expansion of e to a small number, so discount rate is going to be 1%, 2%, then we get that is 1 plus the discount rate. And then the discount rate squared is already, if it's 1%, we're going to 1 over 10,000, so that's much smaller and negligible. Good. Now, how can we interpret the two numbers? So this one is easy to interpret. If I have a nominal a yield discount interest rate of 2 means I put 100 on my bank account, and then 1 year later is 102. Yeah. Now the continuous one is written this way, but I can take the time derivative, and so now I see that my relative increment each day is this discount rate. And so if I say it's a continuous 2% discount rate, it's as if every day the bank adds your about 1/365th of your interest to your account, and this now starts giving you interest also. So it's slightly more interesting. Yeah. So it is, let me say this again. So if this is the way you discount, it means that R is your is the time derivative of your relative increase, which can also be written as the limit for a small time interval going to 0, basically thinking in days rather than in years, and you get your rate every day. But the 2% rate is expressed in percent per year, so you should think of it as the rate divided by 365 days that you get every day. Yeah? Remind you that I said in the first week, it's not because I'm saying I'm driving at 60 kilometers per hour that I'm necessarily driving an hour. Yeah, it's an instantaneous speed, and I can have an instantaneous speed, growth rate that applies to a day, but that is expressed in years. Yeah, so this would be 2%, but it applies to a day, and you would get your interest every day. Good. Long story short, they're very similar and we don't care. Yeah? Good. Then, why is our boat a power function of time? So, as economists, we find that very important. So, let's do the following test. So, you can vote. So you can get £100 now. Normally I have my wallet and I bring, like, give one student like £100. And then but I've lost my wallet. And I'm also a bit, maybe, yeah, no, I have less cash these days. Or 103 in a year. And you like, for this to work, you need to believe me that there is no uncertainty. You're definitely going to get it. Like I write the check, but you can only get it in a year. So who wants the 100 now? Imagine I have a lot of cash here. Yeah, okay. We love it. Good. Who wants 103 in a year? Okay. Good. Yeah. Then now we're going to change the setting. Okay. Who wants 110 years? Or the alternative is 103 in 11 years. So yeah, let's vote A. Who wants to get 100 in 10 years? Yeah. And then who prefers 103 in 11 years? Good. Yes, I love it. So I especially love the people who first vote A and then vote B. Because these are the most human ones. So that was the problem with the human being. So they have a problem. Yes?
I feel like it should functionally be the same thing.
Yes. So if this human arrives 10 years later, this problem has converted into this one by the mere advancement of time. Now you can have like the 100 immediately or 103 1 year later. And so if he changes his mind by the mere advancement of time, it's like me saying I'm going to do it's better to do the dishes tomorrow. And then I'm tomorrow and say, actually, it was better to do it yesterday. The mere advancement of time changes my optimal plan. We hate it. So that's time inconsistency. It's our definition of time inconsistency. And it's bad. Like, so it's very human, obviously. And so we should avoid that human trait. So don't make a plan where just the mere advancement of time makes you change your mind. And so that is why, if you want to have the same answer in both cases, you need a discount rate that is a power function of time. I think it, meaning that each year you should have the same logic of the relative importance. If you're indifferent here, you should be indifferent here, so that the mere advancement of time doesn't change. So it means, this means you have a discount rate of 3%. This means also you have a discount rate of 3%. And if 10 years you need each time a discount rate of 3%, you will get the discount rate to the power 10, or the discount factor, sorry. I'll come back to the factor. So this is the same logic, and so what is observed in studies, psychological studies, is that actually people do something like this, and it's bad. Just remember it's bad, so don't do that. Good. Small remark, it could be that when there is uncertainty, you might be use a smaller discount rate. And then, yeah, we'll come back, we will see the model. Since then in the far future, things are very uncertain, you discount, you become more prudent because there is more uncertainty involved, and you're more prudent in wanting all your money today. Now, the definition of the discount factor, very often written as beta in macro models. So it's just defined as the discount rate. But the exponential of the discount rate times time. So it would be the discount factor would be different for 100 years than for 10 years. No, because time is inside the exponential. And so here we have a discount factor, which will always be 1 for 0 time step. And when we discount at 1%, $100 in or pounds in 100 years is still almost worth $30 from today's perspective. The present value would be 30. But if we discount at 2%, it's merely 50. And if we discount at 5%, it's going to be, less than, more or less 1. Okay? Now, once you go to 200 years, by the fact that this is exponential, this ratio explodes. So the yellow line is the ratio of the value of blue, the 1%, divided by how you value it if you use a 5% discount rate. So if you value climate change at 5% discount rate, you're going to have 3,000 times less value in 200 years for any damage than when you use a 1% discount rate. It becomes very large. At 100 years, you have a ratio of, it's not very visible, but let's say 100 times less. Good. So if I apply the same logic of valuing climate change, a certain integrated assessment models, damages in the future, but they are like shrunk because I've applied this discount factor. Yeah. And so clearly this is a very interesting thing to do. These advantages are much larger than the costs. If I discount at 2%, it's unclear. Luckily, these advantages continue for centuries, so there will be still do a positive net present value to follow this path. 3% no longer. So in this case, at 3%, this climate scenario would be too ambitious. The gains are smaller than the costs because the gains come far in the future. And 5% definitely don't follow this climate plan because you're so focused on today that you don't want to have the reduction in consumption today. So let's now think about some ethical foundations why we should and how we want to set the discount rate and why we should discount. Why is it not zero? Yeah. So in cost-benefit analysis, we look at a potential policy and we say, does that improve social welfare? Yeah. And the social discount rate is then it's a property of the social welfare function, and you can think of it as the internal rate of return that a social project needs to obtain to become worthwhile doing. Yeah, to get a green light. It's that's exactly like I have given you the internal rate of return definition. So this return at which you would set the net present value at zero. And so you can think of the social discount rate as the minimum rate that you need to obtain to give a green light to a project, to make sure the project has more, increases welfare. Good. And so for the social discount rate, we have basically two contenders, but we've made it three. So the two firms are quite related. So first one, think of me or the government thinking of me approving my situation. I want to insulate my attic. Yeah, but I'm going to get a loan. And so in the case that I take a loan by the bank, the interest rate on the loan is going to be a very good candidate for my social discount rate. It means that if the loan stretches out over the same period as my energy savings, I can pay the loan with my energy savings. That would be the condition of a green light. So it's your opportunity cost of funds, and it's a very good candidate to check if this makes sense. Now, I start from my personal situation where I just look at profit for myself. But if you also think as the bond market as an opportunity cost, because investors could not give this bond to the state, but invest it at the same return somewhere else, it becomes the social logic as a required return to give a green light to a project. If the bond market prices things at 3%, and you're gonna do a project with an internal rate of return of 2%, you're destroying welfare because the investor would have done better. You're losing money, no? And so there would be an investment opportunity elsewhere at 3% that's now not done because you're doing your 2% project. And so that is that. If you use this definition. Now, we're very close to the next definition. It's the marginal productivity of capital. It's actually the next step that I was already making with my attic insulation example. So you have to think of the rate of return as the opportunity cost of capital. The capital could be invested elsewhere at that rate. And you have to match that return for this project to create value. If not, with lower return, there is no value. Remind you, in cost benefit, whatever is non-market externality, it's going to be added to your cash flow. So you have each period benefits and costs, but we think about all benefits, all costs to everybody to have a proper cost-benefit analysis. No? And if in that case you don't reach the opportunity cost of capital, you have a problem. Yes.
But the observed marginal productivity of capitals in markets do often not include those externalities, right? So it's kind of like an unfair comparison in that sense, that the social discount rate does include externalities, while the rates observed in the markets often do not.
So exactly. So if markets are inefficient, the return on the market is not necessarily the opportunity cost of capital. And so that is why a lot of people, economists, would then use the social rate of time preference, so the Ramsey rule based on ethical parameters. And we'll start with, we continue, yeah, we'll see this in the next slide. So as a reminder, the Ramsey rule tells you that the discount rate has two components. One is the pure time preference rate. Impatience, all else being equal, 1 kilo, how do I compare 1 kilo of happiness next year to 1 kilo of happiness today? And one good candidate is the same. Yeah. Yes.
Quick question regarding, so if earlier you said we can also use this IRR approach, and I know from different contexts that sometimes that like has difficulties because you don't have a single solution. Now, do you usually just use this more NPV approach to go around that, or what do you do if that is the case? Like if you...
I don't know. I've never seen it. I've seen a paper where like you have always, how is it? For n periods, you will have n solutions if you include the complex solutions. I have to think harder if you have several solutions. In practice, it's very rare, I would say. Good. So we have the pure time preference rate, could be 0. So if I say like actually for my washing the dishes, I value my time today the same as next year, and I haven't massively increased my salary or so, then this would be 0. The other is more fundamental. If you're inequality averse, and we know society is richer in the future, but they have lower value because they have low marginal utility. They are rich, so we care less. Economists always care less about the rich than the poor because the marginal utility becomes low if you're rich. And so that's this second element. We're going to come back to this. Yeah. Inequality aversion, the wealth effect, and so I saw, in the US, I made this joke. So people hate economists for 2 reasons. First, they hate them because they discount. Be aware, they're going to discount. People are not going to like it. And second, because they say we never take inequality into account. But there is a contradiction there. We mainly discount to take into account inequality. The second term is bigger and more fundamental. Personally, I'm very happy with 0 here. And so, inequality matters. And so people can hate us for discounting, or they can hate us for not taking into account inequality, but not for both. Good. So, normative approach. So we have this welfare function. Just for the ease of the exposition, I'm going to write this as a sum. because you'll see later. But you remember, so this is actually the same, no? This is just switching to discrete time. So this is a pure time preference rate. The same utility, no, I'm thinking about utility, kilograms of happiness, and how do I discount that? And so it's satisfaction, unrelated to how wealthy you are, yeah? And so it's the pure time preference rate that comes in. It's part of the definition of your welfare function. Then we're going to assume that I invest a small amount, let's call it £1, and then I get X time my £1 back, yeah? And for notational ease, I'm gonna convert this X into an internal rate of return. So I define R as the internal rate of return, meaning that if I take the example of 3. So I get 3 times my pound back. So I get £3 here, and I'm going to write this as an internal rate of return. I will then also need to specify after how many years. So if it's after 20 years, I get 3 years back. You put in 20 here, X is 3, and you solve for R, and you'll see that this has an internal rate of return of 5.5. Okay? This is just for notational ease. The X is converted into an implicit return. So what is my change in welfare? So it costs me epsilon, £1. I get 3 epsilon. Yeah. Now this is discounted at the pure time preference rate. And how do I value dollars? I have to convert that back to utility. To convert it to utility, units of satisfactions or utils or kilograms of happiness, I apply the marginal utility. Yeah, it's very small. It's £1, so I can just apply the marginal utility. In the notes, you can see why this is a marginal utility, but it's very intuitive. You know? Now, initially, I have the marginal utility related to my consumption today. In 20 years, this might be different. Let's assume it increases. Yeah, I get better and better. I get richer. Or society gets richer. And that's it. So what do I do to find my social discount rate from here? We're almost done. Any idea? Let me help you. So the condition, what is the minimum rate of return is when I set this to 0. Yeah. So when I set this to 0, that will then give me the, I'm looking for the internal rate of return that makes me just indifferent. Yeah? Good. So then set it to 0 and reorganize, and here we have this Ramsey rule. R is the pure time preference rate, and then we get this wealth effect. But this is the more general form. Yeah, it depends on how my marginal utility has increased. If I get rich, marginal utility will become very small. And so then this becomes very small. This becomes below 1. The log of below 1 gives you a negative number, and so you'll get this wealth effect. Now, let's think a bit more about utility functions. So So utility functions are always increasing and then also concave. But there are different levels of concaveness, and we're going to use the isoelastic utility function. We've used it in week 1, we've used it in week 2, I think, and so here it is. Now, for notational, for the ease in my graph, I've subtracted 1 here. You don't need to do that, but that makes that they are all like nicely comparable. They all have an asymptote to 0. They're all negative. Utility is negative. We don't care. So with this logic, I can shift it all up or down. Adding a constant to your welfare function doesn't change the welfare function because it's all about trade-offs. And so it's always about slopes of the welfare function, not about the levels. Good. So, small remark, once this would be eta is 1, then you get the log. It's a special case. So therefore, marginal utility is consumption to the power minus eta. And so what is, I've already shown in week 1 that if you calculate the change of the marginal utility, the elasticity of the marginal utility with respect to consumption, you get your eta. Yeah, that's the mean. So by how much percentage does my marginal utility change if I increase my consumption by 1%? That is this. You can write it this way. It's a different way of writing it. It's just the value. Like here we have the derivative of the marginal utility with respect to consumption. That's the second derivative. That's the only thing that has changed. So what is the interpretation? Imagine it's very high. So now for 1% of increase in consumption, my utility might decrease with 2%. It's 2. I have made the green line is eta is 2. And so if I look at consumption here, I'm poor, here I'm rich, there is a large contrast between the two slopes. Whereas if I take a low eta, half, that is the orange line, it's actually the square root of consumption, then the contrast is very mild. My marginal utility is very similar, even if I'm poor or if I'm rich. Yeah, low inequality aversion. Now, you can apply that within your own lifetime. So it gives you then the desire for consumption smoothing. So your inequality aversion within your life, you want to be the same level of wealth, of consumption at each point in time, meaning borrowing a lot when you're young and unproductive, and then paying it back when you're old and when you're like in peak performance. Let's say my age, yeah. Then let's say younger than me. Yeah. Over time between generations, so that is the one that is going to interest us for climate change. Yeah. So the inequality aversion between generations, and so if you're very much against inequality, then actually you care much more about the current generation that is poorer. Yeah. And then interestingly, it's also your inequality aversion between good and bad states of the world. So if you think about yourself and you don't know how your future unfolds, you're gonna make like trajectories. I imagine a good trajectory, I'm rich, and a bad trajectory, I get fired and I'm poor. And so the inequality aversion between these two possible outcomes is your risk aversion and it's going to be the same parameter. In simple models, this is the eta is also your risk aversion. That's why it's called the constant relative risk aversion utility function, because eta is constant. So the macro guys, they always call it the CRRA. Is this clear? I've forgotten this one. So it's also your inequality aversion when you're thinking about transfer between people. Yeah. So how much more do I value an extra pound for a poor person versus an extra pound for a rich person? Yeah.
Aren't we sort of taking then like a weak sustainability perspective, like implicitly, because we sort of measure this in terms of like, okay, how much income do the people actually have? But there's also like a natural capital perspective to the world, and future generations like will be much poorer if you sort of value it like that a bit. So you could, I feel like you could actually argue for like
the opposite.
Yeah,
I love it. Yes. So so let me answer in two times. So careful with the Ramsey rule. If the future generation is suffering and lives less well than us, the discount rate becomes negative. And that's very possible and valid, and so it is possible that the discount rate is negative. That's the case whenever the future is worse off than us. So if you think the future is worse off than us, then you should include negative discount rates. Careful with welfare, so the welfare function becomes infinite. You cannot optimize infinity. There are technical problems related to that, but for specific projects, it's very easy. Then environmental discounting, we'll see it on the last slides. So exactly, you might have high consumption, but very bad environmental quality, and then you get an extra term in our Ramsey rule, which can be negative. Yeah.
I had a sort of similar related question. So if like, this is like looking at like total wealth now and then in the future.
Yeah,
right?
Particularly consumption, yeah.
Okay. So then if like the future, there's more inequality, like would that be taken into account or like not necessarily?
Yes. I've actually left out these slides. I had too much. I have always too much. You've noticed that, no? So there is a way of correcting the discount rate for the inequality. Now, the simple case, and that is exactly exact, you can just think of a project who is paying, and you apply this person's marginal utility, who is getting the benefit, and that might be a poorer person or a richer person, and you just apply to that the gains to that person. Now, if is this like tax to get a service in the future, you sum over all marginal utilities. That is how you get a cost in utils, and then for the gains in the future, you see to whom it goes, and you apply the marginal utility of each person. And then you get everything in utils, and it's perfect. Like it has fully taken into account inequality over time and inequality within periods. So that is why, and it will then, in a simple framework, you apply eta to everything. There is just one, and that is what you will do under the veil of ignorance. So that's this ethical framework where you try to imagine that a person doesn't know where it's born, when it's born, or in which social class it's born, and that if that person is indifferent to your policy, then the policy is also, that's your ethical basis. And so the veil of ignorance, the veil of ignorance would set an equal eta everywhere. Because you don't know when you're born and where, these two would then create a similar logic. And also, the same logic for risk. Good. So we like CES utility, so the one that I've just been explaining. So let's simplify our formula. We started from here, and now we know the exact form of marginal utility is C to the power eta, and then power of log can come in front, and then the log of CT over C0, that's what still needs to be developed. Imagine that I define JG as the mean growth rate of my consumption, then G is by definition this term. Yeah. So here I say by this equation I have defined G as the average growth rate. I rewrite it, get this, and so I can get my Ramsey rule here, which we already had. But G can be the average growth rate between paying for your project and receiving the outcome. And it's also true for non-optimal consumption paths. So we found this already, and then we said in the Ramsey growth model that this would be the net productivity of capital. But this was an optimized model. What we have now shown is that on whatever consumption trajectory you're at, if you're evaluating a marginal project, this is going to be your discount, Ramsey ethical discount rate. Okay. Some projects are not marginal, so climate cost benefit, and so then this growth rate of consumption becomes exogenous. If you have more damages, at some point you're going to grow slower, and so then this J becomes endogenous. Happy? Questions? There was some text. So now, what are your ethical parameters? So this is all about ethics, no? Like, and there is no good or bad or like a wide range of parameters are justifiable. So I did research on this. So initially, so my family, they're quite left. And so I was on skiing holiday and I said to the family, like, what do you think about this idea that economists typically do? So if you're very averse to inequality, then and the future generations are rich, so you put more value on the poor current generation. And if you put that in a climate model, you're gonna want a hotter climate and do less. That's because you care less about the future. So if you're inequality averse, you do less for the climate. Now, it was an insult, obviously, no, because I was saying that they would that they were inconsistent or anyway. Then I thought, maybe there is people do not apply the Ramsey rule, and so then we started testing this with an article, and so apparently they do, but less than within periods. And then we also checked political parties. So the more right-wing, but this is in Belgium, like the right-wing in Belgium, in Wallonia, it's relatively center. Think of it as center. They actually apply the Ramsey rule more like the economists, and then the left people would be a bit more, very high inequality aversion within periods. By the way, everybody had very high inequality aversion within periods, but then over time periods, they apply lower inequality aversion. Good. So let's see what is your parameter. So this is from this research, no? And it needs to be, imagine you have, you're working for the government and you have a project to improve soil fertility, green fertilizer, very good. The effect on the environment is neutral, let's say. It's mainly about the fact that if you do the project, the harvest of these farmers will be better. And imagine that we're talking about a marginal improvement. So it's not, you can just apply marginal logic, it's a small project. The farmers don't pay, the effect is temporary, let's say 5 years. And so you have to choose between two regions. So one region is already quite fertile, but farmers get 3,000 net per month. And they get 9 tons per hectare of harvest. Or you can go for the sandy region, less fertile, people are less rich, 2,000 per month, 6 tons per hectare harvest. And when you choose the sandy region, increasing fertility on sand is harder. So you're going to get less effect. So good. So you have two options. This is the income of the fertile region or the harvest, and you can add 10 tons here, but it's a small amount. Or you put the project in the less fertile region, and you would get then 3 tons extra harvest. Who prefers project to invest, apply the project in the fertile region? That's A. You can now raise your hand. You all have to choose one of both. Yeah, good. And then 1/3. And who prefers to invest in the sandy region, like do the project in the sandy region? Not everybody's voting. Okay, good. 1/3. So amazing. So there is obviously no solution to this. So it's an ethical barrier. So you accept a smaller cake if it's more equally divided, or you want to go for the big cake, but then it's less equally divided. And at some point, like we all would go for, like imagine that I make this 1 to versus 20, like everybody would be here. If I make this like 7 to 10, everybody would be here. So that's obviously a trade-off. People find it very hard to make ethical trade-offs, but as economists, we are very much trained to do this. And so if you were hesitating, so here is the calculation. So you have an eta of 3 if you were hesitating. And then larger above 3 here, below 3 if you are really. Then imagine a different case. There is no inequality. It's just you can do the project immediately and they get 10 tons extra. Or you can wait 20 years and then they'll get 12 tons extra. What is the most meaningful project? Weirdly, these farmers have constant income. Or you think of it as 2 regions, but they will have all like 3,000 pounds per year. Okay, it's just wait. Okay, who wants A? Good. Who wants B? Who prefers B? Yeah, so a slight preference for this. So your discount rate is slightly above 1%. Here is the calculation. So if you're indifferent, then your pure time preference rate, because there is no inequality here, is going to be 0.9%. By the way, these were the so in the research, these things start changing, but these were the averages of the population of my research. So that gives you an intuition Then we have the proper discounting with inequalities. So you can do the project initially in the low fertility region. Then you would yield 5 tons. You can also do it in 20 years in a high income region. High, meaning 50% more. It's not like super high, no? And then you have 10. Who wants A? Good. Who wants B? Yeah. So we are slightly more unequal averse than the population in my research. And so then if you were really hesitating, then you have an eta of 1.26. So it's lower than in what we found in the within period inequality. Yeah, that was came out of this research. Good. And you can then do the opposite for declining income, and you get something. So, quick point. So if you have an eta of 1, it means that this is the case. Imagine that you have like an African country, very poor, and then another country 10 times the consumption. Then you value $1 10 times more. That is for an eta of 1. If your eta is 2, if you have a difference of 10, sorry, a ratio of 10, so African country versus European country, then you would value it 100 times more. Meaning, in some contexts, this has been done as an experiment. I'm a bit in disagreement with this experiment, but it's called the leaky bucket experiment. You would then be ready to tax 100 in Europe to be able to give €1 in Africa. But from my research, there was clearly gains and losses are different. And so I think the leaky bucket experiment is a bit, doesn't take into account that people are very sensitive to what is a gain and what is a loss. So just to give you some interpretation of what the eta actually is. Good. Do we need a break? Yes. Let's give like an 8-minute break, like 10 past 5.
Because I was like an They literally asked me, yeah, if you were being aggressive, and I said, no, I don't think so. I don't know. Too late. Like, it was to be honest, it didn't like so weird. Like, so
I know, it was very weird when you asked.
Like people were letting us know we would have added a +1 your gala invitations.
I think they're going to say they're worse off.
These are very others.
would apply
Yes,
right?
Yeah.
Which it might not be
economists, I
rational.
have results for economists. They think
We need like fast.
no, 1.5. Only 1% of experts think yeah. Most people I meet, they don't think
When you pick the you like want to die. No.
I don't know, in the 80s people were really thinking that we would exterminate atomic bomb and then like end of
Calling me side. Yeah.
It's not the first time.
yeah, there's this from this
I mean, if it was a quick one, like 2 minutes, like seconds.
Curiosity's museum. It was just like
I don't think we're gonna go
it is not
actually no, I actually
I mean, if it's
yeah,
those animals.
right now.
I tried and I made it. You never know whether it's like chemically or something, but it's still a lot of this.
It's like
Next time. You left a
private one, and there was another one reviews.
and apparently drank the other half and drunk on
It
it.
was like it was just like super bizarre.
Where and see
In Bethnal Green.
Ich glaube, es war ja
Lions, and they have a human skeleton attached there. It was just like bizarre.
It's not absolute.
It's an absolute yeah. 70% of it.
In my mind,
And I was just like, no, thank you.
and then it comes back.
That's too much.
And then it comes back.
I think that's the worst place I've ever been in London.
Ich kenne das so, ich habe das Snap gekauft. Das ist, glaube ich, so mega geil.
See the lights. The lights are
Und jetzt 2 Jahre ist der Fan einfach jetzt
It's American. So honestly, film is not. Or something like that. Have another British player.
some
It's don't know, but another join your seats. Okay. Thank you. Particularly the lady, yeah, here. Join your seat. So, positive approach, market interest rates. We've been thinking about consumption and setting the discount rate with using consumption growth rate. But there is also like the production side. What is the opportunity cost of using capital or savings or for this project? And so we know that actually, if everything is optimal, there is no contradiction. We found that actually this consumption-based discount rate is equal to the net productivity of capital. But what if it's not the case? And so, yeah, again, if financial markets are optimized, then it's just equal. And so then there are economists who have said, like, let's take a non-paternalistic stance. Who are we to say, like, how people should discount? We just look at how people in real life would discount. And so I give this small example. Let's see here. So let's see. You have this. Imagine, your dad makes this reflection. He can save at 4%, which is a bit large, high, but let's just for simplicity, I do 4%. He can go with you on a restaurant, pay £100, proper restaurant, like a bit expensive, or he can die in 50 years and leave you 740. The fact that the 4% is observed means that the average dad is indifferent, or the average investor, if not, the 4% would not be an equilibrium rate. No, if everybody thinks it's better to give heritage to your kids, they would save, and this would then go down. No? So, by looking at interest rate, we know how people discount. And so the reasoning goes, if you observe the interest rate of your dad, you know which one he will prefer. Now, obviously,
the tax rate comes in also in there.
This is a simple world without tax, because if not, you would then have this typical tax for companies. There is some kind of tax advantage. No, I'm mixing things up. So, taxing inheritance would push to consumption, and then there is less capital, marginal productivity of capital goes up, and this one will go up. Anyway, this is how the argument goes. No, I'm not saying that your dad is, oh, by the way, your mom can also give you inheritance. By the way,
Good. So I'm just trying to make sure you understand arbitrage. That's my only point. What do we do if you have two selves? You want things, you say, yeah, but I should have a no arbitrage logic because arbitrage is bad, like it's inconsistent. And then you say, but when I start thinking about ethics, I'm at 3%. I observe 4% on the market, like I have this problem. So the argument here is, it's fine to have difference, but try to keep the difference modest. Because, so one reasoning is, I don't care what the crazy guys in the finance world are doing, like, fuck the 4%. I have I'm gonna, and this would be the logic, no? Because you can say, this is the result of market failures, or maybe because in high inequality or what. By the way, the investors is a minority, etc., of the population. So you go with that. Makes sense. But then it also implies too high discount rates. The private sector is underinvesting. That's the implicit conclusion of your ethics. In your ethical world, there would be higher investments so that this comes down. Can be. Then careful in the sense that whenever your government could tax less the company and the company would invest that privately, you improve welfare because it's going to be invested at the market rate. Or if you have to get raise bonds at 4%, you might crowd out capital that was actually having an investment at 4% in the private sector, and so you're decreasing welfare by squeezing even less capital, like by having even less capital in the private sector. So you get arbitrage opportunities. The same if you would do climate change at 3% and wealth, health policy at 4%, that's not consistent. And so that would mean that whenever you take away money from the climate budget, give it to health, you're improving welfare. So that is a non-desirable property. You want something that is, like, has no arbitrage opportunities within the government at least, and then also between government and private. You don't want large arbitrage opportunities. Good. So keep them not too far out. Keep them not too far apart. So historically, this has been a huge dispute. This is Stern from the LSE, writing the Stern Review in 2006, the first very alarming report on climate change. Nordhaus, Nobel Prize winner, Yale. And so Stern was proposing a very low discount rate based on the Ramsey rule. And then Nordhaus was proposing 5%. And as a result, social cost of carbon that he proposed was only $35 per ton. And so a very modest climate policy was that he was advocating for. Whereas Stern found, a social cost of carbon of 200 because of, among other things, because of this discount rate. By the way, you know Simon Dietz, no? He was also on the Stern review. Then my colleagues did an expert review on they looked at 180 experts that published in top journals. And so the many economists of these experts for long-term projects of a century, they would discount it between, let's say, 1 and 3 or so. Yeah. And so Stern was very low. And Nordhaus was at the very high end. Yeah. And there has been over time a tendency to discount climate at a lower discount rate. But that is unclear why that is. Yeah. Good. So then different governments have set discount rates by law, because it's very easy. If you want to think this bridge should be built, you just use a low discount rate and it's fine. Definitely, like you can prove the utility of the bridge by just choosing a low discount rate. The utility of any investment, no? Against this manipulation or cheating, several governments have set, make investment books, green books. Yes.
I have a question regarding how we actually estimate the Ramsey discount rate, like in an econometric way. How does it work? Do we do an experiment, or we look into the preference of people in transactions, or how it is estimated?
Yeah. So I did this research with the type of questions that you've been answering. I'm not sure if I'm a huge believer I mean, this is obviously interesting and tells us something, but that is one way to go. You can also incentivize in certain experiments. People would then get 1 chance out of 100 that they really get the outcome that they vote for, if it's money for them. But normally people discount in a way that's quite irrational, I would say. As a Minister of Finance, I would not necessarily ask the people, like, how many taxes do we want to pay, or how much debt should we build up, or so it's quite complicated. So I think that is why this positive approach is attractive. We observe rates, and so you can then say, okay, imagine this and that market failure. Now I'm going to adjust for that. What kind of rate comes out? Yeah, but many people also say it's about ethics rather than observed preferences. That's why the example of the dad inviting you for a restaurant or an inheritance makes sense. Immediately, like, what is best? This choice, actually, when I invite my kids for a restaurant, I'm not thinking about the discount, like the return on my bank account. I just invite, there's a bit of a feeling. Yeah, now you're in a problem, like, because I just don't invite it based on feelings. And so, yeah, the thing that is tricky. Now, uncertainty. So we're going to start with a safe project. So the project has, we know what the outcome is. A safe project in an unsafe world. Okay, this is about what is happening. How do you think of your utility in the future, and the marginal utility, and the fact that you don't know exactly how much you will consume. Let's assume 2 periods that are affected. We're back with our initial idea. So you have this welfare function. Now you have a project and, no, sorry. We have the expected welfare of the future. This expected, we're going to further simplify, saying there are only 2 outcomes, a good and a bad. Two possible options, and so then I multiply each outcome by the probability, and then we do the same logic of we invest £1, we get for sure £3, internal rate of return of 5.5, and we get this welfare effect. But the change is now that I take the expected value of my future marginal utility. And so I set this to 0 to get my indifference point, the minimum return that I need to be indifferent for the project. And so the expectation is the only change. I get the same formula, but now I have the expected value of marginal utility. So Jensen's inequality, that is what is gonna drive our difference, yeah? So again, we keep it simple and we have two outcomes, possible futures, each realized with 50% likelihood. So I'm consuming C0, quite irrelevant, and I could be poor, I could be rich. Now, if I just take the average outcome and I look at my utility function, I get in this upper bar of the risk premium. I know for sure that I'm getting this. I would be on the utility function having this. Now, in this risky case, it's different. I take the average utility I have the utility in this case times a half, the utility of this other possible future times a half, I'm getting in this point. So then I add them up, divide them by 2, I will get to this point, which is visually on the straight line. And so this difference between a sure outcome and the risky outcome is my risk premium. That's the change and so you'll see that if you have a concave function, that the uncertainty will always bring your outcome down. So the expected utility is lower than the utility of the expected consumption. Okay? And that's it. So this is called Jensen's inequality. So if it's concave, we'll have the case that the utility of the expected utility is lower than if you would just take the expected consumption and take the utility of that. That's true for all distributions, for all concave functions. Now, our discount rate uses marginal utility. Yeah, marginal utility is convex, I'll show you. And so we get the opposite relationship. Let's show this quickly. So I have consumption 1, consumption 2. This is my marginal utility. Very high when I'm poor, low when I'm rich. And so my marginal utility, my expected marginal utility is higher than the case without uncertainty. Good. So this pushes this expectation now increases the marginal utility of the future. I add this risk premium, and so this will then decrease the discount rate for a certain project. There is a minus sign. Let me say, is this clear? So it's negative, but it becomes less negative because this factor, which probably is lower than the marginal utility today, but it's going up, coming closer to the marginal utility today, so I discount less. So let's give a closed form solution for a simple case. Consumption between two periods. So the change in the log of the consumption between 2 periods is the growth rate. I can rewrite it this way, so you can see x tilde is the growth rate. And let's assume that this x is normal with mean mu and sigma variance sigma squared. So then there is a supplementary note that explains this. I'm just going to give you the result. So this was the result we had already. So that we have the growth, the expected growth rate here, and this should actually be G, but let's subtract from that. So we get this extra term. This is a prudence term. It's going to be negative. I discount at a lower rate. Since since I don't know the kind of future I'm in, and the bad states of the world are particularly bad, I'm afraid of these, I insure myself by discounting the future at a lower rate. I put more weight to the future because I don't know how I'm going to do. Yeah? Should be quite intuitive. Now, and so you can call it precautionary savings. I save despite the lower rate because I want to make sure, I want to insure myself in the case this future is bad. Now, for developed country economies, this is actually quite small. So we don't have that much volatility in our consumption. And so the variance is very small. And so you don't get a big correction. In this case, for the UK, 0.075. It can be bigger for very volatile countries with a lot of variation. But even then, it's a minor correction. Now, it becomes bigger if these shocks are persistent. So remember, in the preceding slide, each year we have a new random normally distributed shock. Like, we're more afraid of a scenario like the end of the Roman Empire, 1,000 years without growth. Okay, but that is a very correlated shock, no? Like, we have a bad shock and another bad shock. For 1,000 years, we have bad shocks, so to say, because I have a positive mu in my model. So that makes you much more cautious. Whereas in the preceding slide, every year you can have, you have a new draw of a random, normally distributed variable. Nothing lasts. Now we give persistent shocks. So we have our standard shock, but now we add a shock Y with persistence. Yes.
Then to the point before where the shocks are normally distributed and they keep reoccurring, wouldn't that then be symmetrical? So if we expect that worse shocks can happen, we can also expect that the same shocks of the same magnitude in a positive direction can happen.
Yes.
Then why does that lead to precautionary savings? Just because the magnitude of the shock gets bigger, or?
No, the Jensen's inequality says if you have 100 and you get a shock -10, you're in a territory of higher marginal utility. If you get a 10 more, you're in a territory of lower marginal utility, and so you care more about the -10 than the +10 because of the concavity of the utility.
So then if the eta would be very small, that would that effect would lessen.
Exactly.
That concavity is much better.
Yes. To answer your point, so in the note I explained that actually the growth rate is not mu. It's a log normally distributed growth rate, which has, I think, mu plus 1 over plus a half sigma. It's like in finance with Brownian motions, the geometric Brownian motion has an average growth rate that is different from the mu. Persistent shock. So this growth rate, we had already mu, we have a normal shock, nothing changes, but we add a persistent shock. And the persistent shock means if I have a crisis today, if I had a crisis last year, I'm likely to be still in crisis. So this is an AR1 process with phi as the persistence variable. Good. And so now the formula is, if you are just looking at one period, then nothing much changes. You just add up these two shocks, and that is going to be very close. But as you discount farther in the future, this persistent shock is going to have a higher weight. And so if this is like 0.9, you get 10 times the effect of the persistence shock, because it's persistent over time and it's this like long-lasting bad outcome, and now you get even more prudent with the future. And so this is an argument for declining discount rates. If you have persistence in your shock, then you get declining discount rates, and that is a well-established agreement on that. So here are different studies. So 4 studies, and they would start at discounting at 4%, and then they go to 2% over 100 years. After 200 years, some are at 1.8 or so, or 1.5. Yeah, with this logic of bounded uncertainty over time. Question?
Yeah. Persistent makes the shock harder, which decreases the discount function, no?
On average, not much is happening. But if you have persistent shocks, the set of future outcomes becomes much larger. So it's also the case that a Brownian motion will already give you infinite variance on the. So like if I have a Brownian motion, you would get like families, and it would like give you something like this. It goes out, and in infinite future, you have infinite variance. But if now, like each time, I don't have this a new draw. A bad draw tends to be followed by another bad draw because I have this persistent shock. Now I get wider options. And so this one is going to have a very high weight because I have very low marginal utility. And so you just expand the set of outcomes with these persistent shocks.
If we have such a persistent shock, could we just say that the utility we expect to have in the future is lower? Because, like, in this case, with like the Roman Empire is gone and we have no growth. The outcome after the Roman Empire is gone was pretty bad, right? So could we just like formulate it in a different way than just saying it comes every year again? It's just, or maybe where I come from like where my thoughts come from is the long-termists. They often say, like, I don't know, we talk about AI and we assume that AI will destroy the world. So this is going to be really, really bad. And even if we discount it, it's still going to be really, really bad. So we really have to do a lot. And isn't that kind of the same? Does that make sense?
Yeah. So there are two things. The one that I try to, and which is the biggest mechanism, is that the more you're uncertain, the less you discount. And so this is Jensen's inequality. That is it's an important mechanism that you have to understand. Now there is a second technical issue, but now I'm afraid that I'm getting the sign wrong. So if you have the expected value of e to the power x, x is your growth rate, we call it x tilde, and x goes at
X is mu plus sigma mu dt, yeah, no, I'm writing it in Brownian in continuous time. It doesn't make sense. The only point that I want to make is that your true growth rate is affected by your variance. So G will be mu and then a correction factor. And the logic is that if I have a, if I start from 100, I have a 50% increase, I'm at 150. Then I have a 50% decrease, I'm at 75. I'm not at 100. Although my shocks are symmetric, I do a plus 50 shock and a minus 50 shock, I'm not back at my initial point. And so that is a mechanical thing that if you have log normal distributed shocks that are symmetric, they have in itself an effect of pushing the mean growth down, the mean growth rate down. This is a bit too technical. Forget about the second point. Remember the first, Jensen's inequality. We care much more about this one because we have low marginal high marginal utility here. We don't care so much about this one. We're super rich. We don't care about this extra martini that we are drinking on a yacht. Good question.
Short question. This reminded me a bit of this discussion between like level effects and growth effects, so like Berke versus Nordhaus. Is this related, or should we try to separate that in our thinking?
For now, separate. I think they are. Obviously, this is also exponential but would bring us too far. Yeah, it's the logic of exponentials, but then the discounting of that damage function is not different. Good. So we've said it, and in practice, risk aversion is much larger than inequality aversion, and I would call the risk aversion no, let's start with this. In observed studies, you can measure risk aversion. This is larger than the inequality aversion over time. So the eta for risk is larger. There is a way to get this into your framework. So if you do climate cost-benefit analysis, I use this setting. It's very hard to understand, and so we're not sure. I'm just telling you it exists. Yeah. So, what is your level of risk aversion? Let's do a small test. So, consider a bet. You get one chance out of two, a loss. So you're tossing a coin, and 50% chance at gain. Assume you have 2,000 per month as an income. Your consumption is 2,000 per month. So, what is your, imagine the toss, if you lose, you get minus 50. What is the gain that makes you indifferent with, to play?
Double.
100?
Yeah, percent, yeah.
Okay, so you would accept a game where you lose 50 for the rest of your life and you win 100 for the rest of your life. Who would accept that game? that bet? Come on. You lose 50 and you win 100. Who accepts? Yes. Who refuses?
A single game or a repeat game?
Let's make it a single game. But actually, I think in our framework, it would be the same. which is obviously wrong, no? Because let's make it easy. A single game. I have money actually, cash there. Who accepts lose 50, win 100? Just now. Okay. Who refuses? Guys. 100% return. You should all accept, no? So people are very. So for the record, you should accept this game. This is it's bad for me. It's good for you. So, but let's get a bit more serious. So if for a 50 loss you require a 100 gain, you're off the scale. Like, we don't consider that rational. But like in finance, they use relative risk aversion, an eta of 6 or 8. Now look what happens for 200, a 200 loss, a 10% reduction forever. It's a bit like a risky game. Or infinity forever with 1 chance out of 2. If you refuse that, you have an eta of slightly above 8. And so, what can I say? You should be careful with 8 and 6. I'm happy with 4, but we find it relatively hard to match that to rational behavior. Even here, if it's 4, or let's say with 6, you refuse a game where you lose 300 or you win infinity. And so that is, maybe that's a preference. I cannot prove that is irrational, but I can only make you aware that you rapidly go into very big trade-offs. Yeah. Then catastrophic risk. I'm going to say just one thing. There is this nice paper, Barrow 2006. It just looks at big disasters. And so it's mainly World War I, World War II, but by adding these to portfolio logic, he can match out this puzzle that we see. Yeah, we can match returns on financial markets that seem too risk averse, but actually by adding disasters, you go a long way in explaining observed market risk aversion. Yeah. Now, important, we have been discussing a safe project in an unsafe world. Now we look at an unsafe project. So most projects are obviously not certain, and so you get risk in your project. You had a question.
That paper by Barrow that looks at tail risks, or is that the same or not?
Yes. So by having shocks, the tail distribution becomes better. Discounting a risky project. So higher or lower discount rate? Yes.
I think lower.
Mm-hmm. So you have these 2 options. Expected, one is risky, the other is not risky. For which one do you want the higher internal rate of return to be indifferent? The higher. So the risk is a handicap, and you want a higher risk rate of return, like in stocks. Stocks are riskier, you want a higher return. That's the logic. So you all know the CAPM, capital asset pricing model. So it's a simple, not super simple model about that tells you that if you have a risky return, your expected return, your required internal rate of return in expected value, because now this project is no longer certain, so you take the expected value, is your risk-free discount rate, the one that we've been discussing, and then you have this difference between the return on the correlation between the return on the market and the return and the risk-free. Sorry, this is an error. This must be the sorry, this is not an error. So the excess return on this is the key logic. So beta is your. That's also in finance. They talk about beta. Yeah. So this is this covariance between your market return and the return of the project. If the project is very pro-cyclical, like stocks, doing very well when you're actually very rich, and then doing very bad when you're getting fired, then you want high returns. Good. Now, last point is about environmental discounting. So there was this remark already, like, what if actually we're going to consume a lot, but actually there is also the environmental quality goes down, and actually we're not better off. And so that matters. And a slightly simpler question is to say, like, what if I'm like assessing the appreciation for a walk in a forest, but I'm assessing it in the future, and there might be less forest in the future. Or maybe there's just the same forest, but we're so much richer. And so when you're discounting in dollars, the relative price or the shadow price that people pay, that is associated with walking in the forest is going to go up. The willingness to pay to be in the forest is going to go up, and that needs to be taken into account. Good. So assume that we have now utility depends on two things: consumption and environmental quality. Same welfare function for the rest. Now you can say we had already this formula for consumption. You can do exactly the same logic for the environment. You say, I have a project, I'm going to reduce environmental quality by epsilon. I'm going to increase it I'm going to reduce it by 1. I'm going to increase it by 3 in the future. How do I assess that? What is my minimum internal rate of return that this project requires? And so you get exactly this. And so it depends on how much you value this marginal effect in the future compared to today. I see that I've switched to continuous time. We do that in a seminar. Yeah, this switch from discrete time to continuous time. And so I can calculate this, and you'll see that we'll do it in the seminar. We get this eta that we had already, inequality aversion between environment today and environment in the future. And then we get the cross elasticity. Does my appreciation change for a walk in the forest change if I'm rich or poor? That's the cross elasticity, and that then brings in a term that depends on how poor or how rich you are, the growth rate of your consumption. For consumption, this is now also this is symmetric. we had already this. So delta plus eta times G. But now there is going to be a cross elasticity. How does I appreciate my consumption when I have less environmental amenities? Remind you, this is a project, doesn't affect the environment, you're just bringing consumption into the future, and then you would use this discount rate. Yes?
Wait, sorry, the GE, is that the growth of the value gained from the environment?
Yes. So it's the growth of the quantity of environment that you have.
Oh, so it's the environment that grows, not the value attributed to that environment.
Exactly.
So here we have the growth or the decrease in marginal utility from the environment. If the environment is deteriorating, this marginal utility goes up, and this becomes a negative term, and we start discounting the environment at a negative rate. Yeah? But that is thinking in hectares of forest or in number of species rather than in dollars. How to explain this? And now I'm going to make the link between the hectares and the dollars or the pounds. So we're going to define willingness to pay as the price of environment. So if I'm willing to pay $10 for a walk in a forest, or to have this forest exist, then this is, the price is defined as the marginal utility of this forest compared to the marginal utility of the $10. And that's a general case. So prices is the relative marginal utility. And we can then take the time derivative of the price. Price will depend on consumption and environment. So the time derivative is just, this is the total, the time derivative. We've done this in the seminar, we'll do it again. And so we can then define the income elasticity of environmental quality. It's how much does my willingness to pay change as a percentage if my consumption goes up by 1%. And I can then, this is the change of the derivative of the price with respect to consumption. These are just, I bring this to the other side, and I get this expression, that the marginal change of the price with respect to consumption is this cross elasticity, the income elasticity of the environment times P times C. We can do the same for environment. So then we get the same expression, but it's now the marginal price with respect to the environmental quality. And then I get this, I can combine both results and so the last step is that these things, for certain utility functions, they are similar, and we're going to think of the constant elasticity of substitution. I'll explain in the seminar which function that is. It's the most common function we use for utility. And so then these income elasticities are just the 1 over the elasticity of your utility function. They are the same, and you get this result that the price increases at the difference of the growth rate. We'll see an example of this in a seminar. We had a publication in Science last year arguing that this should be at least 1, and so that you should take into account that if you value things in the future and they are not increasing, for example, forest in a country where forest is stable, then you should assume